Get really good at reading position versus time graphs, velocity versus time graphs, and we're going to look at interpreting motion in graph form. Okay, so this is just kind of a quick introduction to these two types of graphs, but we're going to get really good in those in the next couple weeks. Okay, so this is a position versus time graph. Position versus time. So this means as we're moving, every 0.1 second we move 20 centimeters. Okay, and I know you probably can't read those tick marks quite as well, but we have a constant straight line. What type of relationship is this? What'd you say? Yeah, like a direct correlation, so a linear relationship. Okay, when we have a straight line here, when we have a good even slope, that means we're moving at constant velocity. Okay, so a position versus time graph, the slope of a position versus time graph gives you velocity. Okay, that's important. Slope of a position versus time graph gives you velocity. Okay, because when you find slope of a linear relationship, it's delta y over delta x, okay, or rise over run. On this particular graph, what variable for velocity would go on the y-axis? Okay, I know that's kind of sounds weird. This is our position right here, okay, and position is measured in delta x. And what goes on the x-axis here? Time, right? This is rise over run. And this equation we know right here is velocity. Okay, so that's the explanation for the slope of a position versus time graph giving us a velocity. Okay? Yeah. Okay. This velocity versus time graph shows us that we're moving at a constant speed because it's not changing here. It happens to be 200 centimeters per second. Since we have no slope here at all, our acceleration would then be 0. Okay? Very good. Let's look at some graphs that are non-constant velocity. Okay, that means we are speeding up, we're slowing down, maybe we're staying the same, but non-constant velocity. Okay, so if you can't quite read, velocity is on the y-axis and time is on the x-axis. Okay, so let's talk just about the motion, what's happening throughout this graph. Okay, and if you want to write these down as we talk through the different points of them, you can, that's fine, or if you just want to listen and soak it up, that's fine too. So from point A to point B, what's happening here? Yeah, it's getting faster. It's going from 0 meters per second to 20 meters per second. It's speeding up or accelerating. From B to C, it's doing what? Constant speed. So it's like setting cruise control. Okay, they sped up and they set cruise control. From C to D, what happens? Accelerating again. So gas pedal here is constant velocity. We're staying the same. Then we do what? Yeah, we hit the brakes, right? We start slowing down. F to G is constant, and then G to H is accelerating again. Okay, so velocity versus time graph, those slopes give you our acceleration. So if we have a positive slope, that means we're speeding up. If we have a negative slope, that means we are slowing down. Okay, very good. All right, let's look at acceleration. Acceleration is a change in velocity. Acceleration can be both positive and negative. Okay, so when we're speeding up, we consider it accelerating. When we're slowing down, we consider it decelerating. Okay, but more often than not, we'll just talk about acceleration in one general term. Okay, and you can have both positive and negative acceleration. Sorry. And here's our equation, of course, for acceleration. So change in velocity over change in time. Do we know the units right off the bat? Yeah, Thomas, what do you think?
So isn't it like meters per second over
Meters per second. Yep, good. So velocity units are meters per second divided by seconds again, which gives us meters per second squared. Okay, meters per second squared. Only the second unit is the square. Okay, meters are not squared here. Acceleration is meters per second squared. Okay, I'll give you a few seconds to get it written down and then we'll work through it. It says during a race, the sprinter increases from 5 meters per second to 7.5 meters per second over 1.25 seconds. What's the sprinter's average acceleration during this period? All right, so what I started doing here on the side is making my list of variables. And this v sub 0 is what your book labels initial velocity, okay? V sub 0, so that means velocity at time 0, basically, is what it's saying, is your initial velocity. V would just be your final velocity, T would be your time. So let's talk about what variables each of these are. What's V sub 0, or our initial velocity? 5, good. And our final velocity is? 7.5, and our time? 1.25. All right, very good. So we're going to plug this into delta V over delta T. Are we ever given an initial time and a final time? No, right? They don't need to tell us that time starts at 0. Okay, so you're just going to get one single time that's going to always go in as your delta T. Okay, so acceleration equals 7.5 minus 5 over 1.25, which should give us an acceleration of about 2. Very good, and we just said our units were meters per second squared. Okay. The unit difference between meters per second and meters per second squared is very, very, very important, okay? And you should be able to start picking variables out of a word problem just based on their units, okay? So here, even if it doesn't really say that its velocity increases, it just says a sprinter increases from 5 meters per second. So we have to know what the meters per second unit means, right? We have to understand that that is velocity, that connects with velocity. Okay, all right, let's try another one. So Marissa's car accelerates at an average acceleration of 2.6 meters per second squared. Calculate how long it takes her car to accelerate from 24.6 to 26.8 meters per second. All right, so I like to make my list and my margins. I think I've said that before. All right, and what's our shortcut if we want to solve for this bottom variable? Do you guys remember the shortcut? Did we talk about this? The shortcut here is to switch these two places, okay? So you're going to do your subtraction, but then you just move t to the top and move 2.6 to the bottom, okay? So you'll take 26.8 minus 24.6 and divide it by the 2.6, which would give us t equals 0.8, okay? Do we agree? All right, and what's our units for time? Seconds, very good. Okay, if we had been dealing all with kilometers per hour for some reason, we have to make sure that we label our time correctly, okay, in hours, but everything matches here for seconds, so very good. Velocity and acceleration. These two things are not the same at all, not the same, okay? Velocity tells us the rate at which the position changes. Okay, so how many meters you're moving per second, how fast your position will change. And acceleration tells us how quickly the velocity changes. Okay, it tells us the rate at which the velocity changes. Let's go ahead and try another one here. Car accelerates along a straight road from rest to 75 kilometers per hour in 5 seconds. What's the magnitude of the average acceleration? What's it mean when it's asking us magnitude? Magnitude is just the number that goes into it, okay? Acceleration is a vector, which means it must have what two things? Magnitude and direction, okay? So when it's asking for the magnitude of something, all it's asking for is the answer, right? It's asking for the number. But we have to remember that acceleration is a vector, so it needs both magnitude and direction. The reason that we know it's a vector is because velocity goes into it, and we know velocity is a vector, which must have magnitude and direction, okay? More often than not, acceleration can be express direction in just positive or negative, okay? So we can just pretty much keep it at that. All right, so what's the first thing that we need to do here? We have any idea? Yeah, we've got to convert this kilometers per hour to meters per second, since our time is in seconds. So about 20.83 meters per second. All right, so we know, what's our initial velocity here? 0, right? Because it says it accelerates from rest. Our final velocity we know is 20.83, and our time is equal to 5 seconds. Okay? So that means acceleration is equal to final minus initial over time. Do we agree? 4.17 or 4.167? All right, very good. Any questions about that so far? To meters per second. So 1 kilometer is 1,000 meters. 1 hour equals 3,600 seconds. For every single kilometer per hour to meter per second conversion that we do, will the T-chart look the same? Yeah, this part of our T-chart should look the same every single time, right? So all we have to do is do that math. So take 1,000 right now divided by 3,600. And what do you get? 0.2778. That's where we're going to round it to. This right here will be our shortcut to go from kilometers per hour to meters per second. So right now, if you take 75, multiply it by that, we should be getting about the 20.8 something that we got the first time. So this shortcut is something that you can use or not, it doesn't matter, but this makes those conversions just a little bit quicker rather than having to make a T-chart for every kilometer per hour to meter per second. Okay, so when you want to go from kilometers per hour to meters per second, you multiply. If you need to go back the other way, what would you do? Divide. So if you need to go from meters per second to kilometers per hour for some reason, you would divide by 0.2778. Okay? Questions about that? Again, that's optional for you. That would be something that you would have to memorize. I won't give you that shortcut because you know how to solve it the long way. But if you want to memorize that and use it, that's fine. Okay? Very good. Okay. So with a partner, I want you to think about these two questions. and we're going to talk about them here in just a couple minutes.